In Chapter 7, we are going to talk about solids, liquids, phase changes. We're going to focus mostly on solids and liquids and then discuss how we go from a solid to a liquid. And here is kind of the breakdown of the sections of the chapter that we're going to discuss. Let's start with general properties of the condensed phases, and the condensed phases refer to solids and liquids. We know that matter exists in these phases, 3 phases, and we've already talked about this. We have solids, we have liquids, and then we have gases. The solids and liquids are referred to as condensed phases, and they differ from the gases in terms of how strong the intermolecular forces are between the molecules and how close the particles are to each other. As you can see, solids are very ordered. The particles are very close to each other. Therefore, the intermolecular forces are higher than in the liquid phase or even in the gaseous phase as well. And you can see that in the liquid phase, it's got some order, but not like the solid phase. And the molecules are a little less ordered, not as close to each other, but there's still enough of the intermolecular force to keep the particles in the liquid phase. And then we go to the gaseous phase here, and you can see how far apart those particles are from each other, and therefore the intermolecular forces are not as pronounced in the gaseous phase. Let's talk a little bit about some definitions. First of all, we divide solids into 2 different categories, amorphous solids and crystalline solids. Now these, just from the name, we can deduce what they really mean. So A stands for none, basically, and amorphous stands for shape. So the particles in amorphous solids do not have a highly ordered arrangement. They are just bonded together, but they're not really bonded in a highly ordered or regular way. So here is an amorphous solid. It's got parts of it that are more ordered, but it's not really, in general, that ordered as, let's say, this beaker, for example. This is quartz we use it to make glass. In a crystalline solid, we have the molecules or the ions that make up the solid are highly ordered. Obviously, it's the opposite of amorphous solid. And the properties depend on the nature that the part of the particles that contain. You can see how highly ordered this arrangement is versus this one. We have some order here, but not like this one here. So this will dictate how ordered they are, and the types of molecules or particles that make up that solid will dictate its properties. We then divide the solids into 2 more categories. We can have ionic solids or molecular solids. From the name, once again, what is an ionic solid? It's a solid that is made up of ions. So most ionic substances, they are solids at room temperature. And this is due to the electrostatic forces that holds the ions together in a very ordered 3-dimensional array. So not just 2-dimensionally, but even 3-dimensional array. And we have alternating cations and anions that occupy these ordered structures. Molecular solids, on the other hand, from the name as well, are made up of molecules, not ions, but molecules. Typically, they will be covalent bonds. And those molecules have, instead of electrostatic forces now that hold them together, they are held together by dispersion forces, and we talked about what they are. We can also have molecular solids that have molecules that are polar. In those cases, the molecules are held together by dipole-dipole interactions. And here is an example of a molecular solid. So this is ice cubes. So if we just zoom in and we look at the arrangement of the water molecules in the ice, you can see that they're very highly ordered. And there are, in this case, not just dipole-dipole, so they have dispersion forces, dipole-dipole forces, and hydrogen bonding between the water molecules. We can also have atomic solids. The atomic solids make up really all the metals that are solids at room temperature. They consist of very ordered three-dimensional array of these atoms of the metal, the element. The metallic bonding is responsible for holding the metal together at room temperature, being a solid. What happens in metallic bonding is that if this is a metal atom, this is going to share all of its electrons, its valence electrons, with all of the other atoms that are in the solid. And what happens then is you get this cloud of electrons that are shared by all of the atoms in the structure. And we have positive metal ions that are left behind, and then this cloud of electrons, a sea of these valence electrons that are shared by all of the positively charged metal ions. The valence electrons that are being shared collectively, because they're not really limited to just one atom, but they are free to move around the whole structure, that allows the metals to be such good conductors of electricity. Remember that to conduct electricity, we need to have either free ions or free electrons that can move freely. And this is the case for any metal. That's why metals are very good conductors, because they are atomic solids that have metallic bonds. We call them metallic bonds, where the electrons, the valence electrons, are shared equally by all the atoms in the structure, the three-dimensional structure. And what we have left behind are these positively charged metal ions that are sharing all the sea of valence electrons. This makes for a very, very strong forces that hold the metal ions together, and therefore metals in general have very high melting points or boiling points because of these electrostatic attractions, these intermolecular forces between individual ions of that particular metal. Network solids, or covalent solids, are those solids in which the atoms are connected by covalent bonds, and they can be even stronger than ionic bonds. Here's quartz. This is what quartz looks like, and these are all repeating units of SiO2, but they are bonded, covalently bonded together, and therefore they're very strong. Here's the difference between carbon, so arrangement in two different forms of carbon. You may not know that really what's in the pencils, even though it says lead, but what's in the pencil is really carbon. And diamonds are really carbon, but they are just different structures, different arrangements of carbon atoms within these structures. Here, carbon assumes these hexagonal shapes, And they form these sheets in planes, basically, and then they're held together by intermolecular forces, these sheets of carbon that are arranged as hexagons. And those sheets then are held together with each other by these by these intermolecular forces. And you can then see how we use pencils to write. What's being smeared off is these planes of carbons, and that's what's left on the page when we write with a pencil. When it comes to diamonds, however, the structure of carbon is tetrahedral, but all of these carbons are bonded together, covalently bonded to other carbons. Here we have sheets of covalently bonded carbons, but the sheets themselves are not covalently bonded. They're just they're interacting with each other because we have dispersion forces between these, but they're not covalently bonded top sheet to bottom sheet. Whereas here, all of the carbon atoms are covalently bonded and they form these tetrahedral arrangements. That is why diamond is one of the hardest, actually the hardest known structure to us. We use diamond to cut anything else because it is so strong, and this it's due basically to this arrangement of the carbon atoms in the structure of the diamond. They are covalently bonded to each other, and that's why they're so strong. Here is a table that illustrates the types of crystalline solids and their corresponding intermolecular forces. So you can look at, okay, I have ionic. In ionic solids, we have dispersion forces and ionic bonding, so electrostatic attractions. When we have molecular solids, they can be nonpolar molecules, can be polar molecules, or polar molecules with hydrogen bonding because they have that NH, or FH bonds. They can have just dispersion forces if they're purely molecular and nonpolar. They can also, if they're polar molecules, they can have dispersion forces and dipole-dipole interactions. And then when we have polar molecules that can hydrogen bond, then we have dispersion forces, dipole-dipole, and hydrogen bonding. So dispersion forces are for nonpolar molecules, dispersion and dipole-dipole for polar molecules, and then dispersion, dipole-dipole, hydrogen bonding for those polar molecules that have these types of bonds. When we have atomic solids, they can either be metallic or nonmetallic. The metallic solids have dispersion forces and metallic bonding. And remember, the metallic bonding is very, very strong because it's almost as if you have this electrostatic attraction, but it's between all of these positively charged ions, atomic ions, and this sea of valence electrons. So they can be very strong. If it's a nonmetallic atomic crystalline solid, then all we have is dispersion forces, not very strong. When we get a network of crystalline solids, we can have dispersion forces and covalent bonding. And we know that if the network has covalent bonding, that can be even stronger than ionic bonding because those are not just electrostatic attractions, they're sharing those electrons and they're very strong. Here's kind of a flow chart to help you determine the types of solids. So first of all, the question that we ask is a substance an element or a compound? If it's a compound, then we have to determine whether it's an ionic or molecular compound. If it's ionic, it will be held together by ionic bonding. If it is molecular, then we have to figure out, is the molecule polar? If it isn't, then it will just be held together by dispersion forces. But if it is polar, do the molecules contain any of these bonds? If they don't, but they're polar, then the crystalline solid is held together by dispersion forces and dipole-dipole interactions. If they do have these bonds, then they have dispersion forces, dipole-dipole, and hydrogen bonding. If we only have an element, on the other hand, then we have to ask ourselves, is the element atomic or molecular? If it is molecular, then molecular crystalline solids are held together by dispersion forces. If it is atomic, is the element a metal or a nonmetal? If it is a metal, then we have metallic bonding. But if it is a nonmetal, then we only have dispersion forces. This is kind of a flow chart that will help you determine what the type of solid is. Here is a sample problem for you. Determine the type of crystalline solid that each substance will form under the conditions and list the intermolecular forces that would hold the solid together. You will use the flow chart to determine what types, whether you have an element or a molecule, a substance basically, whether the element is metallic or a molecular. If it is an atomic, basically atomic solid, is it a metal or a nonmetal? If it is a molecule, is it an ionic compound? For example, is this is a molecule. Is it an ionic compound or is it a molecular compound? Same thing with here. What about I2? And if it is a molecule, is it going to be nonpolar, polar, or is it going to have hydrogen bonding? So for that, if it is a molecule and you need to determine whether it's polar or not, you will have to do a little bit of Lewis-Dot structure to help you with that. Okay, give this some time and some thought, and don't be discouraged if you don't get it the first time, but just follow all the steps. This is kind of a review of Lewis-Dot structures, molecular shapes, intermolecular forces, and the types of solids that we're just learning. So we're building on what we have already talked about.